So hello everyone, this is lecture 18 for the quantum mechanics. In the last lecture we were discussing about the operators and I have told you the information about the operators and the definition. And for the different kind of observables I told you what will be the operators. Okay. So today first we will see the questions I have given you. Okay. So this lecture is gonna be a little bit long. So let's start. First question I gave you was this: the wave function in 1D position space corresponding to a quantum mechanical particle is given by. So wave function is given in 1D and it is given for where a is greater than 0. So what we need to find is find the probability of finding the particle lies between minus a to a. So first we need to find the probability of finding the particle. So see, for the probability this was your operator. First we need to check if this function is normalized or not. So how can you check this? Find the square of this wave function and put the limit minus infinity to infinity and integrate with dx. So let's see. We need to do this and value of this will tell you if this function is normalized or not. If this came out to be 1, then we call that function is normalized. So square of this function will give you 1 upon a exponential minus 2 mod x divided by a. So this will be your psi square. Now what you need to do is take the limit. Now this mod will make this limits separate, means it will for minus infinity to 0 this will be minus x here, and for 0 to infinity it will be x here. So we divided these limits, so it will be minus infinity to 0 1 upon a exponential 2x by a dx plus 0 to infinity 1 upon a exponential minus 2x by a dx. Now see, integration of this will be exponential 2x by a and divided by 2 by a, so it will be a by 2 here and same here, and this will be minus again, minus from here. So see, this a will cancel out. Now you substitute the limit, minus infinity is 0, so at 0 it will be 1 upon 2 and minus at minus infinity it will be 1 upon infinity will give you 0 here. So from here you will get 1 upon 2 and from here again you will get 1 upon 2 and this will be 1, means this function is normalized. Now what we need to do is find the probability of finding the particle between minus a to a. So this is 1, so we just need to do this x1 to x2 psi star psi dx. So this will give us the, so limit will be minus a to a and 1 upon a, this is psi star psi will be psi square, so this is exponential minus 2 mod x divided by a. Now again divide the limits, minus a to 0, 0 to a, solve the integral and put the limit, you will get this 1 upon 2 1 minus exponential minus 2 1 upon 2 minus exponential minus 2 plus 1. So you know how to integrate, so I am just leaving that part. So this is same as this, so it will be 1 upon 2 plus 1 upon 2 will give you 1, so it will be 1 minus exponential minus 2. So this will be your probability. Now second is find the probability of finding the particle outside the region. So we have the probability between this region, so 1 minus, because total probability is 1, so 1 minus this probability will give you this one. So 1 minus this will be exponential minus 2. So this will be the probability of finding the particle outside minus a to a. Now the third question is find the value of b, so that the probability of finding the particle minus b to b is 0.5. So probability is given and we need to find the value of b. So now it's the same as we did here. So now this probability is given 0.5 and limit is minus b to b. So we just separate this limit here. In place of minus a we will write minus b0 and 0b and solve these integrals. So this will give us 1 upon 2 1 minus exponential minus 2b by a and minus 2b by a. So these are same, so it will be 1 minus 2b by a, and this probability is given as 0.5. Take the log, it will give you minus 2b by a equal to log 1 upon 2. Log 1 will be 0 minus log 2, so b will be here a by 2 log 2. So this will be your answer. Let's see the next question. So here your more large number of concepts will be clear from this part. So the wave function of the particle that is confined in 1D region is this. So wave function is given 1 upon root L sin pi x divided by L, and this is for the 0 to L. So function is defined only between 0 to L, otherwise it will be 0. So what we need to do is we need to find all of these 6 things, that is position, expectation value of position, expectation value of momentum, x square, p square, del x, del p and del x, del p. We need to find all of these. So first for the x, we know what we do, it will be just this formula. For this x we will just put x inside and psi star psi and this, so this will give us the average value of this. So let's do the thing. So here is your solution. First let's find the value of this. Okay, normalizing factor. So what is, if this function is normalized or not, let's see. So psi x is this, so take the square of this, it will give you 1 upon L sin square pi x by L dx. Now for minus infinity to infinity, this function is only defined between 0 to L, otherwise it will be 0, so limit will be changed to 0 to L. and 1 upon L will be taken out because this is constant. So 1 minus cos 2 pi x divided by L. This 2 is again out, and now you will integrate this. It will give you x minus sine 2 pi x divided by L, and this will be 2 pi by L here. So L by 2 pi becomes. Now put the limit 0 to L, and after solving this you will get 1 upon 2. So the value of this denominator is 1 upon 2, and this function is not normalized. So we need to put the value of this as 1 upon 2 because we find it this value is 1 upon 2. So now we will find the values of these numerators, and we will divide by 1 upon 2, then we will get our expectation values. So for x, substitute x inside and put this function in the left hand and right hand side and solve the limit. Let's see for the expectation value of x. So for this we will use this formula. We know the value of this is 1 upon 2. Let's solve for this one, numerator. So this function is psi and x inside. So psi star is same as psi because it is not complex. Now we will solve this. It will give you 1 upon L. So first this function will be defined between 0 to L only, otherwise it will be 0. So limit will change to 0 to L because minus infinity to 0, 0, 0 to L, L to infinity. This will be 0, this will be 0, and we need to solve only this one. So now you will use what? You will use here sine square pi x by L will give you 1 minus cos 2 pi x divided by 2. So it is the formula cos 2 theta equal to 1 minus 2 sine square theta. Now solve this. 2 will go this side, 1 upon 2L. Now you will divide them, and here you will use the integration by parts. So first take this function as first function, this is second function, and solve the limit so you know how to integrate. So you will get these values, and it will be here, it will be L by 4 plus this thing, and when you substitute L and 0 it will give you this value, and after solving this it will be L upon 4. So the value of this numerator is came out to be L upon 4. Divided by 1 upon 2 will give you expectation value of x, that is L by 2. So we calculated the expectation value of x. Let's find for x square now. Second question was here. For x square we will just put psi function this side and psi function this side, and it will be x square. So this time we need to solve for the x square. So we will do the same. Limit will be 0 to L only, and the square of the function will give you 1 upon L, psi and psi star. So we will solve this thing, and it is just a simple integration. So and this will be 2 will be outside. Take these functions separately, and this will be this. Now this here you need to apply the integration by parts 2 times because this is x square. So first differentiation will give you 2x, then again integration will give you x equal to 1. So you can solve this by integration by parts. So after solving this is just the formulas I have applied. In the last you will get this 1 upon 2L, L cube by 3 minus L cube by 2 pi square, L square by 2, 1 upon 3 minus 1 upon 2 pi square. So this will be the numerator value. Now the complete x square average will be L square 1 upon 3 minus 1 upon 2 pi square because this is divided by 1 upon 2. So it will be this. Now for the momentum. So you know what is the momentum operator. So for momentum I have told you. You will use this one minus I h cut del by del xi. So we will do the same in place of operator. So this was your formula. So in place of this you will write minus I h cut del by del x. So I did the same. So this is your psi star and psi, and inside you have I h cut del by del x. This will be operating on the psi. Now take the 1 upon root 12 outside because this is constant. Sin pi x by L will give you cos pi x by L and multiply pi by L. And then again this will be sin pi x by L, cos pi x by L will give you divide by 2 multiply by 2, it will give you sin 2 pi x by L, sin 2 theta equal to sin theta cos theta. Then you know how to do the integration. It will be cos 2 pi x by L, and 0 to L will be limits, and when you substitute these limits it will give you 0. So expectation value of momentum will be 0. Now for the p square you remember I told you this is this. For p square psi, if you remove these 2m here, so it will be nothing but minus h cut square del square by del x square. So we'll take the second order differentiation here for the p square. H cut square del square by del x square. So this is the psi and this is psi again. So you will take the second order differentiation of this. So it will give you this. Now again you will integrate and put the limits, and this will give you h cut square pi square by L square. So this will be your value. Now you need to divide it by 1 upon 2. So what you will get? You will get 2 h cut square pi square by L square. So p square value is this, and p is 0. Now for del x, I told you what is uncertainty. The formula is x square average minus average square. So you already find this value. This was this minus L square by 4. and this can be written in this form. This will be resolved to this simple equation. Now del x will be this, means uncertainty in position is this, L root 1 upon 2L minus 1 upon 2 pi square. Now uncertainty is momentum will be this, this will be del p square minus p average square. So this was 2h cut square minus p average was 0. So this will be your value. So under 2 h cut pi divided by L. So uncertainty in momentum will be this. Now I will tell you in detail about the Heisenberg uncertainty principle, but from here you can check this. You remember the formula, that is del x del p should be greater than equal to h cut by 2. So let's see if we are getting the same thing or not. So we know del x and we have del p. So multiply this. It will give you L under root 1 upon 12 minus 1 upon 2 pi square. Multiply this. Now when you solve this, many things will cancel out. The pi will be cancelled out. So it will be this. Now let's find the value of this, because you know pi is 3.14. So square it and minus 6. This will give you 0.8 h cut. Means this complete thing will give you 0.8 h cut. Now if you divide by 2 and multiply by 2, it will be 1.6 into h cut by 2. Now see, this del x del p equal to 1.6 h cut by 2, means this is greater than h cut by 2. So this satisfies the Heisenberg's uncertainty principle, that is del x del p is greater than h cut by 2. So here it is greater than h cut by 2. So it verified the uncertainty principle. So now you know how to find the uncertainty, how to find the expectation value. So I given you quite good examples. Now let's move forward. So now we will start about the tools of quantum mechanics. So this is all the mathematical part of the quantum mechanics, where you should learn the language of the quantum mechanics, that is maths. So because in the quantum mechanics we will study all the maths, because there is nothing physical to understand. So we understand it in terms of maths. Let's see. I already told you Dirac delta function. Del x equal to e to pi iota x p dp. So you must remember this formula. This x will be delta x and p dp. So remember all the terms here. Now you know what is the Dirac delta function. You can go and watch again that lecture. And now today we will discuss about mainly orthonormal functions. So what are orthonormal functions? Two functions f1x, f2x are orthogonal if orthogonal or orthonormal both are same thing, if their inner product is 0. Now what is the meaning of inner product? So it is nothing but if these are two functions and they can be complex also, then the inner product is take the conjugate of this first function and multiply with second function. So if this came out to be 0, then they will be called the orthonormal function. Okay, so it can be different also, same also. So that's how you can check. Now we can take an example and we will we will discuss this notation. This is Dirac notation for the wave functions and the eigen functions. So just ignore this now. I will tell you what is this, but you can write this thing in this form. So let's take an example. f1 is sine 2 pi nx divided by L. f1x is this and f2x is this, cos 2 pi mx divided by L. So these are your two functions. Let's check if they are orthonormal or not. So you need to find the conjugate of first and second. So conjugate will be same because these are not complex. So you just multiply them and find the integration. Now see, this can be written in terms of minus L by 2 to L by 2. So and this function inside this dx is, this is odd function, because f minus x will give you equal to minus fx. So limits, and by this seeing this function, this will be 0 for any case n and m, because this will be always odd. So for any value of n and m, this value will be 0, means these two are orthonormal functions always. Now we will see what is the use of being orthonormal. But you must now remember that what are orthonormal functions, means not what are, means how you can check if the two functions are orthonormal or not. So you must remember that thing here. So now we have discussed when we discussed the wave packet for the wave function. So we have discussed that there were a lot number of individual wave functions. Okay, means we represent them in terms of e to pi iota xp1 for have the p1 means for the particular state, and for the particular state it was momentum p2. So we can represent them means it was phi 1, phi 2, phi 3, phi 4. So we represent them in terms of these. So let's check if they are orthogonal or not, means in terms of we represented our wave function, if they are orthogonal or not. So let's find the inner product. So it will be multiply this with this and take the conjugate of 1. So it will be minus iota and this. So it will be e to pi iota p2 minus p1x. Now see, this is your Dirac delta function. This complete thing is Dirac delta function. It will give you del p2 minus p1. So see, if P2 is not equal to P1, then this will always remain 0. And when P2 equal to P1, it will be infinite. Means it will exist for P2 equal to P1 only. So normally they are not they are individual states for the wave function. So that's why they will always be different, P1 and P2, P3. So we'll say that these all are orthonormal. How? Because they will be 0 always, because they are not same, and for each state we will having a different momentum. Okay, so that's why they are orthonormal. So remember, in the wave packet, let me tell you this thing. We discussed this thing. For a particle, this was your wave packet, and this is made up of large number of waves, and we described them in terms of these. So these are your states. So phi 1, phi 2, phi 3, these are for the different wave, these are the wave function for different waves, individual waves, and they all have a different P1, P2, P3, and we already proved this, that they are orthonormal, because all are different, so it will be 0. Now what is the use of being orthonormal? Why we are saying every time that it is orthonormal, it is not, and why it is need to be orthonormal? So let's see. Now if they are orthonormal, then you can represent your wave function in terms of these wave functions very easily, because they all are linearly independent of each other. When two functions are orthonormal, they will be independent of each other. That's why we need to take them orthonormal, where these phi 1, phi 2, phi 3 all act as the basis vectors. Now what are these basis vectors and how we can write this? So I will give you an example which you already very familiar with. So you know Euclidean space, that is vector space, we know x, y, z axis. So there you represent any vector in terms of a1 I cap, a2 j cap, a3 k cap. So any vector can be represented in these I, j, k terms. So these I, j and k are called the basis vector for the Euclidean space. Okay, and I, j, k can represent any vector in this space. Now see, if you find the inner product of I, j, j, k and I, k, what you will get? Inner product is nothing but dot product simply. So I dot j will give you 0, j dot k will give you 0, I dot k will give you 0, because all are orthonormal to each other. So we can represent any vector in Euclidean space in terms of these basis vectors only because they are orthonormal and they are independent of each other because of being orthonormal. That's why we need to take them orthonormal. And same we did here in the quantum mechanics. We have taken all the waves, individual waves which are made, and these states as orthonormal states. So these will be orthonormal states. Then we can represent our wave function in terms of these, means any wave function, it can be any wave function possible in the space. So we can describe that wave function in terms of these states. Okay, these basis vectors, that is phi 1, phi 2, phi 3. Now this is the same as we describe in the Euclidean space, and where these functions are described, we call that space as Hilbert space. So remember that when you have these phi 1, phi 2, phi 3 n dimensional space, this is called. You don't need to, means not physically, this is not physically observable thing, because there can be n dimension possible. So as we discussed in the Lagrangian, in the classical mechanics, this is the same thing, means you have the infinite number of dimensions possible. Okay, so in that dimension you can describe your, and that dimension space is called the Hilbert space, where you describe the wave function. So let's see some things about the wave functions. Not the wave functions, we will see more about the vectors first, because I will give you a new definition for vectors here. So linear algebra is building block of means vector algebra is the building block of linear algebra. And you know how a vector is defined, like this. Any vector in the Euclidean space you can describe. Now see, if anybody asks you what is a vector, then you will say that anything which have magnitude and direction is called the vector. So that is the basic definition in maths. But see, this is not always need to be true, because if you consider about the direction, then there will be only 3 direction possible in the physical space we see. But when we discuss the vector in terms of some matrix form, then there will be n dimension possible, which we were discussing here. Now you will see n dimensions, because n orthogonal or n basis vector we have, so they don't need to be in the any space, so they can be in terms of matrix, and that matrix is possible. So just don't see in terms of direction, because then you will be confused that how it is we are getting 4 direction, 5 directions. So that is not possible. This is just seeing them as your matrix. So I will tell you how to see in terms of matrix. So vector is quantity having direction, magnitude, that is the basic definition. Now any vector in the Euclidean space can be represented in terms of ij, and you can write this write this vector in terms of this also matrix, that is 2 1 ij, or you can write this like this in the column vector 2 1. So that will represent your ij, means we will write just 2 1, and that will say that 2 in terms of I and 1 is in the j. So we can write that in terms of matrix also. See, the definition in computer science is different. In that we define as vectors are the ordered list of numbers. So now you don't need to take only three basis vectors. They can be any number. Like I will give you an example how it is ordered list of numbers. Like you have area, and this is your rate of that area. So let's say you have area to 2000 square feet and the price is 40,000. So you can just write a simple matrix 2000 40,000. So this will represent that this area is cost to this. Same for second land, you can describe 3000 45,000. So just this list of these numbers will give you what your all values, because this is the value of A, this is R, this is A, this is R. Now the value of L1 plus L2, we just add them and it will again a same thing, a list of number which will give you land and its cost. So that's how in computer science we will study about the vectors and all. Now see, it can be four things also, means you can find the different variables also for the square feet, area, rate, and accommodations, and you can find the other things also. So that also be represented in terms of this list of number. So you can represent any number inside this, and that variables will be any number. So they don't need to be only three variables. Just like in the Euclidean space we have three axes. So when we have vectors limited to the direction, then we have only three variables. But when we come to the computer science, we can have n variables, and that doesn't mean that there is n directions. Okay, so don't relate dimensions with number always. Okay, so that's why I'm giving you this definition for computer science. So remember this thing. Now see, if you see the matrix, then anything can be written in terms of matrix in maths. Like you have any function exponential x, so it will be 1 plus x square plus 2 factorial plus x cube by 3 factorial. Now see this x square, x3, x0, x4, these all are the basis vectors, and you can represent this function in terms of those basis vectors. How? You will write a matrix 1 1 1 upon 2 factorial, 1 upon 3 factorial, and here it will be 1 x square, x cube. This product will give you again this value. Now you can just write the column vector of this. Just write a column vector of this like you did here. So every term will be related to each of these terms. So you need not to write this thing. You just write a list of number that will give you that this is 1 for x0, this is 1 for x1, this 1 upon 2 factorial for x square. So you can represent any function in terms of the matrix. So now I hope you understand about the basis vectors. So these are the basis vectors, x square, x cube. Same sin x will be, for sin x basis vectors will be x cube, x5. For the cos x it will be x square, x4, x0. So those will be your basis vectors. And same, why I am defining these. So we will do the same thing here in the wave function. We will have the basis vectors and we will define our wave function in terms of the basis vectors, and they can be any number. Now you know from the Fourier series, you describe your function in terms of the sine and cos, and here you have cos 2 pi n x by l and sine 2 pi n x by l as your basis vectors. You define your any function in terms of these basis vectors. So again you have your basis vector. And what is the definition of basis vector? The inner product should be 0. So phi 1 phi 2 will be 0. You know this product will give you 0 always. So now similarly, by this analogy, if psi x is represented in terms of the phi 1 phi 2 phi 3, so those phi 1 phi 2 phi 3 are the basis vectors. I hope you understand now the basis vectors. Now let me give you this thing. Quantum mechanics was formulated in two different ways by Schrodinger and Heisenberg. So first, we have two types of quantum mechanics. Actually, we can study it in two ways. First, in the matrix mechanics, everything will be in matrix. So that was the Heisenberg's picture. So, and that was studied for the discrete basis systems. Means when you have this kind of summation, phi 1, phi 2, phi 3, then you can study complete quantum mechanics in terms of the matrix, and that was for the Heisenberg's picture. But if you have the continuous variables, means you don't have a limited value. Okay, means discrete values. This is continuous. So you can't tell one value different from the other. So that's why you need to means go for the wave mechanics. So here in the wave mechanics we discuss the both thing, the discrete one and the continuous one. Here it was only discrete, but here it is both continuous basis system as well as for discrete, and this is called the Schrodinger picture. So we are studying this actually. So what is the thing? We need mathematical mechanics to study quantum mechanics. The formation of quantum mechanics deal with operators that are linear and wave function. This. So we will deal with operators that are linear. Now operators are linear, so they can be written in terms of the matrix. So we'll see how to represent the operators in matrix. We will see them. Now see, and the wave function is discrete, so we can write it also in the form of matrix. So C1 phi 1 S, C2 phi 2. So these phi 1, phi 2, phi 3 are the basis vectors. And Ci are the component, and these can be complex also. So we'll see in the later lecture that these represent the probability actually. Ci is C2, C3. For the phi 1, this represents the C1 represent the probability for phi 1, and C2 for the phi 2 and all. So as I told you, as you know, Euclidean space is XYZ three-dimensional space, and I, J, K are orthogonal basis vectors for that. Same you have Hilbert space, and it is a n-dimension complex space in which all basis vectors lies as well as all other wave functions that can be written as linear combination of phi x. Now in this Hilbert space, all these phi 1, phi 2, phi 3 exist, and also this wave function which is defined in terms of the superposition of these wave functions, that function is also lie in that space. Like you have the Euclidean space, this xyz define a particular vector, and this I, J, K and these values lie in that space, and this R is again lying in the Euclidean space. Same, this all the basis vectors lying in the Hilbert space, and the vector which is defined as the superposition of those vectors is also lying in the Hilbert space. So it is an n-dimensional complex space in which all basis vectors lies as well as all other wave functions that can be written as linear combination of psi x. So, and the minimum dimension of Hilbert space is 2, and maximum can be infinite dimension for the Hilbert space. Okay, so don't imagine it as some direction. So okay, it's not direction, it's just a something matrix which can have n or the infinite number of basis vectors. So so I hope this is easy for you now. Now you can represent any wave function like psi 1 in terms of the basis vector, that is phi 1, phi 2, phi 3. Some second function phi 2 also can be represented in terms of phi 1, phi 2, phi 3, and these all are lying in the Hilbert space. Since phi 1x and psi x are treated as vectors, they must follow the rules of vectors. So now we are treating them as vectors, as I told you that these are also the basis vectors, and this is again the same vector, and this is lying on the Hilbert space. So they must follow the vector rules. So what are the vector rules they should follow? Phi and phi 2 are elements of vector space, then phi 1 plus phi 2 will also be the element of the same vector space. Okay, we understand this. And commutativity, so it is phi 1 plus phi 2 should be equal to phi 2 plus phi 1. Associativity, phi 1 plus phi 2 plus phi 3 should be equal to phi 1 plus phi 2 plus phi 3. So I hope you know these things, that's why I am not discussing them much. Existence of 0 or null vector, so there will be 0 vector also exists, 0 phi 1, 0 phi 2, 0 phi 3. Existence of inversion vector means inverse of that vector also exists, means a plus minus a will give you 0, that's how. Rule of multiplication should also be followed. So product of scalar with vectors gives you vector. So a psi will give you something new chi vector. So a psi 1 plus b psi 2 should be given some new vector. So they should follow these rules. Means some scalar will be with vector will give you again a vector. Here also again a vector, and these vector added will give you a vector again. So this is also element of the same vector space. So I hope you understand these things. That's the basic things. So distributivity should also be followed. That is a plus b psi 1 should be equal to a psi 1 plus b psi 1. A psi 1 plus psi 2 will give you a psi 1 plus a psi 2. Now associativity, a b psi 1 should be equal to a b psi 1. Now this is identity element, I psi 1 should be equal to psi, and 0 psi should be equal to 0. So this will be psi 1. So these are the things, these are the properties which these vectors should follow, because we are assuming them vectors, so they must follow these all the properties. Now let's see the Dirac notation. So in Dirac notation we represent the elements of Hilbert space as phi 1, phi 2, phi 3, psi 1, psi 2, psi 3. So all the wave functions are lying in the Hilbert space, all the basis vectors are lying in the Hilbert space. So we can represent this elements of Hilbert space as this. Now see, here we will discuss about the cat and bra notation. So it's like a right bracket. So this right hand side called the cat, and this left hand side called the bra. So let's see what is this thing. So you know what is inner product. So inner product is the product of two functions. That is, first take the conjugate of this psi star and psi. So I told you this is a product, dot product of these two things. Now you need to do the dot product, and we know this psi 1 is vector and this psi 2 is vector, And let's take an example of Euclidean space. We have two dimension ij and r is defined as this. So we can write this 2 3 as this 2 3. Now you have some r2 second function that is also this column vector that can be 1 I cap and the 4 j cap. So 1 4. Now see, you need to find the inner product of these two. So how you can multiply? Because these are two vectors, you can't directly multiply them, because you need to follow the matrix rule. It should be number of columns should be equal to number of row to multiply, but they are not equal. To make them equal, what we do, we take the transpose of this vector. So just take the transpose of this vector, and just like you have this r, so r dot r, to take this dot product you need to take the transpose of this vector. Now 2 3 2 3, only then you can find, because now the number of columns will be equal to number of rows. And taking this transpose is, now this vector is represented by this notation cat. So we call this cat, and this is vector space. Means any column vector, means we know these are the vectors, so any phi 1 phi 2 phi 3 will be represented in the real space by this cat notation. So any column vector, this is nothing but column vector. Now take the transpose, and that transpose will lie in the dual space and will represent that by this bra notation. So inner product is nothing but this. Means you will take this r and this. So this is the inner product now. So that's how, this is nothing but column vector, and this is the transpose of this, and you can take the inner product now, because this is now possible. So that's why we have described these notation, because we have described our wave functions as the vectors. So that's why we need to take this cat and bra notation. So now if this is your inner product, so you will describe your inner product in this term. So this will be psi and psi. So this will be your inner product. Now see, this one will be, this is transpose, but if it's complex, then you need to take the conjugate also. So this term, this left hand side, the bra will be equal to transpose of this and take the conjugate. So it is represented by dagger. So dagger is nothing but transpose and conjugate. So we know transpose is this, and conjugate will also be this. Means take the transpose and conjugate, that will give you this left hand side. And this is in the dual space, this is in the vector space. So now what is a dagger? A dagger is nothing but take the conjugate, means conjugate and the transpose. So that will give you a dagger. So the dagger, a dagger, means dagger of cat will give you bra. So that is the basic thing. Means column vector you have, and when you take the transpose, it will give you a row vector and the transpose of that, and that's how you can calculate the inner product. So I hope you understand this now. I have going in the very much detail. So now let's take an example. If this is the cat, so this will be a column vector. Now you need to find the bra. So it will be, take the transpose first, so 2i 3, and take the complex conjugate. So it will be, I will change to minus 2i, so minus 2i 3. So this will be your bra. And so now you hope you understand how to find the bra of cat. So that's how you can do this. So if this is your c1 c2 and this is cat, so bra of this will be c1 star c2 star, because c1 c2 will be your row vector, and c1 c2 are complex, so take the conjugate also, c1 star c2 star. Now inner product of these will be this, c1 star c1 plus c2 star c2. Now see, this is nothing but probability, and this is also the inner product of phi psi will give you psi square. So this represents the probability. We will discuss this thing in the detail, how this represents the probability and all. So just now you just understand this thing, that what is cat and what is bra, and how you can change the one to another. So now if we understand this thing, and we represented cat as column vector, and we know this size vector and this phi 1 phi 2 phi 3 all are vector in the Hilbert space. So this is also column vector, this is also column vector, this is also column vector. So we can represent this psi x in this notation, draft notation, this way. This column vector psi should be equal to c1 psi 1 c2 psi 2 c3 psi 3. So that's how you will represent now, from now on in the quantum mechanics, your wave function. Okay, so remember this. So this is the same as you did here, 2i cap plus 3j cap. So these are your basis vectors, and this is your vector formed by these, and this is also column vector which is formed by these column vectors. So now I hope you understand how we can write this in these terms. So that's it for today. We'll meet you in the next lecture. Thank you everyone.